This presentation is for the Greeks, understanding the Greeks, and just giving you guys the basics when it comes to the Greeks. Options prices are derived through mathematical equations, and the ability to understand the components of these equations, like the Greeks, is essential for you to become a successful trader. So we're going to kick it off with our first Greek that we'll discuss, and that is delta. The delta of an option measures the behavior, the characteristics, and the value of an option in relation to the underlying asset. Underlying asset is simply what's the stock you're looking at options on. So again, delta is going to measure the behavior, the characteristics, and the value of an option in relation to the underlying asset. Delta is essentially the rate of change in theoretical value of an option for every $1 change in the underlying asset. It's also a hedge ratio. The delta of an option changes as the value of the underlying asset changes. All right, so options deltas are measured between 0 and 100. So think of the underlying stock as having a 100 delta. So to calculate the delta of an option, you have to compare the movement of the underlying asset versus the theoretical value of the option as that asset moves. When an option is deep in the money, as expiration gets closer, it has a delta close to 100. So it behaves just like the stock itself. But conversely, when an option is far out of the money or is about to expire worthless, the delta is close to 0. When an option is at the money, the delta is close to 50. So when you think about it, the stock has a 50-50 chance to move one way or the other. Thus, the delta of 50. And that's what this chart here is illustrating. This is illustrating the characteristics of call and put option deltas as they shift from being out of the money, OTM, to at the money, ATM, to in the money, ITM. And so this shows the relationship of these deltas and how delta is measured based on being in, out, or at the money. Call option delta, let's talk about that specifically for a second here. Then we'll get into put option delta. So call option deltas are positive numbers between 0 and 100. If a call option has a delta of, let's say, 45, and the underlying stock moves up $1, then the theoretical price of the option will move 45 cents. All right, so let's say if the stock FDX, if it increases from $185 to $186, right, that's that $1 move, right? When that stock moves $1, then we know delta will be affected. So if the value of the FDX call option increases from $1.25 to, let's say, $1.80, all right? So then that leaves the delta. Well, the delta is equal to 55, right? That's a 55 cents move. The the stock increased $1, right? The option increased. It moved from $1.25 to $1.80. That was a 55 cents move. And the delta is equal to plus 55. But let's say if it decreased, if FDX moved from $1.85 to or $185 to $184, it went down. And the value of an FDX call option would decrease from $4.65 to $4.35. 30-cent decrease in the option, then the delta is equal to plus 30 cents or plus 30. Now, call options, we talked about put options. Put options having negative delta. So the delta of a put option, its characteristics are opposite to that of a call option. Put option deltas are expressed as negative numbers between 0 and 100. So just like the value of a call delta, if a put option has a delta of 45, underlying stock moves $1, then the theoretical price of that option will move 45 cents. All right. So if it moves 45 cents, let's say eBay, all right, we'll take eBay. If it decreased from $30 to $29, the value of an eBay put option, it will increase from $1.25 to $1.80, and the delta of the option is equal to minus 55. But let's say eBay increased. It went from $30 to $31. Right? Again, that $1 move. That's what we're looking at here. If the value of eBay's put option decreases from $3.75 to $3.50, then the delta is equal to minus 25. Sometimes it's difficult to grasp the negative delta of a put, but think of it this way. If you were short stock, you would make a profit if the stock went down. And that would happen is because owning a put gives you the right to sell stock at a certain price. That is, of course, the price of the asset you own. The put increases when the underlying stock price decreases. It's kind of you're thinking a little opposite once you're dealing with put option delta. But the more you go over it, the better chances you'll have of retaining it and understanding it, and of course asking questions in the various rooms, either options volatility or short-term options. All right, so delta goes hand in hand with gamma. Gamma of an option measures the delta curvature. This is the rate at which an option gains or loses delta over a $1 change in the price of the underlying security. Gamma is very important because it shows us how fast our position delta will change as the market price of the underlying asset changes. Gamma shows how volatile an option is relative to movements in the underlying asset. For example, let's say SPY moves from $2 or $285 to $286, right? Makes that $1 move higher. If the delta of a SPY call option increases from 50 to 55, then the gamma of this option is +5. Right? So remember, gamma, the delta is the speed of an option, then gamma, again, will be your acceleration, right? That 0 to 60. How fast did the option accelerate? Gamma is greatest for options that are at the money. Even a small change in the price of the underlying stock affects the delta of the option significantly. That's that high point on the curve. So gamma is going to be lowest for options that are either deep in the money or far out of the money. Low for options that are either deep in the money or far out of the money. A change in the price of the underlying stock has little effect on the delta of an option. But unlike measuring deltas, the gamma value of an option is the same for calls and for puts on the same strike. If you are long a call or a put, the gamma will be a positive number. If you're short a call or a put, gamma is going to be a negative number. All right, let's talk theta. Theta. Theta of an option is the rate at which an option loses value as the amount of time to expiration changes. And the rate at which an option loses value as the amount of time to expiration changes. Theta is also known as the time decay factor. All options lose value as expiration approaches. Theta is going to be the same for both call and put options that have identical strike prices. Options theta can be a little bit confusing, but think of it like this. If you're long options, you have negative theta, meaning that your option loses some value every day, assuming all other inputs remain unchanged. Time decay is working against you. If you're short options, you make money as time passes and the value of the option decreases. So you have positive theta. Time passing has a positive effect on your short option position. However, the time value does not decrease linearly. As the option gets closer to its expiration date, it loses time value more quickly. All right, so that option decay is going to be exponential, with the most decay occurring the closer you get to expiration. This graph shows you that, right? Notice the numbers along the red line as time decreases, right? So it moves quicker once you get into those last few months, right? 6th and 5th month, it only decreases by 2, and from the 5th to the 4th, 3, but now it's increasing as far as the decay goes, decreases by 18 as we get closer to expiration. Let's talk Vega. The Vega of an option indicates how much the price of an option will change in relation to the volatility of the underlying asset. This is also known as implied volatility. When we discuss option strategies, one of our main focuses will be Vega or volatility trading. Vega is quoted in dollars per percentage point move in the underlying asset's implied volatility. So you would simply count the volatility change in implied volatility and then multiply that number times the Vega measurement. If volatility has increased, then you simply add this value to the option's present value. If it decreases, you simply subtract this value from the option's present value. Let us look at an example. Okay, so let's say the theoretical price of an option is $15. Vega is 0.75. If the volatility of that option moves from 35% up to 36%, then the theoretical value will increase to $15.75. So again, $15 price of the option. Vega 0.75. Option moves up a percentage point from 35 to 36. And theoretical value increases to $15.75. All right, like I said before, you add, if volatility has increased, add this value to the option's present value. The value is Vega. Add Vega to the price of the option. But what about decreasing? Well, let's take the same price of that option, $15. Vega is the same as the last one, 0.75. Volatility decreases, right? But in this case, it decreases 2 percentage points. All right. So now you're going to take that option price, $15, and you're going to subtract it from the Vega measurement. In this case, 75 cents. So you're going to multiply that times 2. Why did I say 2? Because volatility decreased 2 percentage points. So you multiply the Vega measurement times 2. That gives you $1.50. And so you subtract $1.50 from the $15 option price. That is how you get Vega, your Vega measurement. Learn much more about these Greeks and how to apply them to options positions, how to manage the positions. All that is going to be explained and taught to you in the respective rooms, whether it's Scott Bauer or Michael Shore option room. So thank you guys for watching our presentation here in the Foundation Room about the Greeks. And this video will be available for you to watch in the Documents tab, which is that little white folder in the lower right-hand corner of the room. Enjoy the rest of your day, and thank you again for choosing Prosper Trading to help you learn various methodologies and techniques. And if you have any questions for me in the Foundation Room,